Good morning, good afternoon, good evening, depending upon where you are in the world today. And welcome to day 2 of the Digital Twin Consortium Virtual Aerospace and Defense Town Hall. I am David Shaw, a former combat experienced fighter pilot, currently CEO of Intuitus Cyber Corporation, and serving as the chairman for this event on behalf of the Digital Twin Consortium. Supporting me today are the DTC team, namely Karen Quattromoni, Harriet Costa, and Dan Issacs, who is the DTC, a general manager and CTO, and all of these who are hosting this town hall. Thank you for that. Before we look ahead, it is worth reflecting on the strong foundation we built together yesterday. Day 1 challenged us to think differently and act with greater urgency. We opened with a compelling keynote from Daniel Hedema, who is the Director of Digital Engineering, Modeling, and Simulation within the Office of Undersecretary of War for Research and Engineering. Daniel pushed us to challenge the status quo and reframe how digital engineering, modeling, and simulation must evolve to meet today's defense demands. That theme carried forward with a dynamic and highly engaging panel led by Sue Nowicki, who is the Managing Director of Bridgeport Partners and a recognized leader in digital engineering in the aerospace and defense industry. Her panel, comprised of Dr. Michael Greaves, Adam Scheer, Tom Alpott, and Dr. Mark Flantz, explored what it truly means to collaborate, to innovate, reinforcing that no single organization can solve these challenges alone. We closed the day with an insightful keynote from Dr. Mohammed Zulfagari, worldwide technology leader for emerging technologies and telecom at Amazon Web Services. He underscored the critical importance of interoperability as the backbone for scaling digital twin capabilities across complex ecosystems. For those of you who would like to revisit or share these insights, all of yesterday's presentations, along with the slides, were recorded and will be made available on the Digital Twin Consortium website following their download from Bright Talk. Transitioning to today, to day 2, we reflect on yesterday's conference, where we reframed urgency. Today, we advance the execution and continue to stand at the frontier of transformative era in defense acquisition, one defined not just by AI-enabled decision advantage, but by the speed at which we can operationalize it. The mandate remains even more clearly defined as detailed yesterday. Digital engineering and digital twins are not aspirational concepts. They are foundational to achieving full spectrum mission readiness for the warfighter. This town hall, spanning these 2 half days, continues to bring together a global community of leaders across aerospace, defense, industry, and research. Today's discussions build on that momentum, moving from alignment to action, focusing on how we scale adoption, integrate capabilities, and deliver measurable operational outcomes. Our collective objective remains unchanged: to accelerate the adoption of digital engineering across defense acquisition by turning policy into practice, enabling faster system design, smarter integration, and fully connected lifecycle outcomes that directly support JADC2 and DODI 5000.97 for a broader and more resilient operational readiness. As we move through today's session, the focus sharpens. How do we take what we know works, expand it and across programs and partners, and ensure it delivers mission speed? Well, we begin today with a keynote from Dr. Yadunath Zambre on overcoming barriers to adoption. Yadu is a distinguished leader in microelectronics and former chief microelectronics technology officer, currently Emeritus, for the Air Force Research Laboratory. He continues to serve at AFRL in this emeritus capacity. Over a career spanning decades, Yadu has helped shape the Air Force's strategy for resilient, secure, and high-performance microelectronics, advancing technologies that underpin the next generation capabilities in AI, autonomy, and digital engineering. His deep technical expertise, spanning work at Lockheed Martin and other private sector businesses, his strategic vision, along with his leadership in fostering collaboration across government, industry, and academia, make Yadu uniquely positioned to address the challenges scaling adoption today's environment. Following that keynote, Dr. Antonios Kontsos will introduce and subsequently lead a panel on shaping the future of defense digital engineering as the Henry M. Rowan Foundation Professor for Mechanical Engineering at Rowan University and Director of the Digital Engineering Hub. Antonios brings a powerful combination of academic leadership and applied innovation. His work focuses on bridging physical systems with digital representations to enable more predictive and resilient engineering outcomes while building cross-sector partnerships that accelerate adoption and prepare the next generation of engineers. We will then conclude, after a 5-minute break, this town hall with Chuck Brooks. Chuck will deliver a keynote on securing the AI-enabled digital engineering ecosystem. Chuck is globally recognized throughout as a thought leader in cybersecurity and emerging technologies, with over 30 years of experience spanning government, industry, and academia. As an adjunct professor at Georgetown University, he teaches in the cyber risk management and applied intelligence programs and is widely known for his insights on AI, quantum risk, and digital resilience. A prolific author with more than 400 published articles at outlets such as Forbes and the Washington Post, he is also the author of Inside Cyber, which explores how emerging technologies are reshaping security and privacy. Chuck has held senior roles in both government and industry, including positions with the Department of Homeland Security and General Dynamics, and has been recognized by LinkedIn as one of the top technology influencers to follow. As we move through today's session, we will encourage you to submit questions through the chat. Time permitting, we will direct those questions to the speakers to further enrich the discussions at hand. Please note that this is a fully virtual, dependent upon technology event for the transmission and capture of presenters' remarks. We appreciate very much our host, Bride Talk, and your patience should any technical issues arise, and that our DTC team will continue to work diligently to ensure a smooth, seamless, and productive experience for all. Well, with that preamble, let's go ahead and begin day 2. Dr. Zambre, you're on.
Good morning. David, can you see the charts?
Yes, I can.
Wonderful. So I'm going to talk about overcoming barriers to adoption in the area we've been working at Air Force Research Lab for quite some time in electronics. A very, very key topic. I'm going to start with how we've actually overcome obstacles, many barriers to adoption. And so we actually started, and I'll start with the left side of the chart. In the research lab, we actually did 6 different chips that we developed using digital twinning type practices across the 4 years. And that matches the pace of commercial innovation. So much of what the research was about was taking commercial tools and methodologies and applying them to developing electronics. And so that allowed us to develop and implement digital engineering inside of the Air Force to develop expertise. We were able to do quantifiable assurance, which basically means looking at our circuitry and making sure that it didn't have any special gifts that an adversary might have inserted. And we applied it to modernization programs. And so there's actually 3 programs that I'm not going to name here because it's a public audience. But each of them was a Category 1 program, so very large, with very large impact across Air Force, Space Force, and Navy. And what it allowed us to do is having built some internal government expertise, it allowed us to communicate both the methodology, the tools, and the key thing is the benefits across various parts of the life cycle into the programs direct, the 3 programs of record. And so I'm going to talk a lot later in the deck about how that allowed us to improve design verification, speed, and coverage. So being able to test and verify our electronics much faster and get better quality of coverage. Some of the programs dealt with parts obsolescence, a key thing. Much of commercial sector applies these tools mainly for new designs. We in the DoD have, or Department of War now, have a lot of parts obsolescence, which is not new design. And then we learned a lot about accessing intellectual property and the need for it to do digital twinning. So I'm going to move on here. So one of the first questions you have to ask and answer is, what is a digital twin of electronics? Let's see here. Bring that back. And so there's several commercial definitions of what a digital twin is. And the DoD definition, which is defined by the instruction 5000.97, you see listed at the bottom. But a key thing to note is, regardless of which definition you use, and the DoD definition is an integrated set of models that serves in the virtual world, in the computer world, and mirrors basically what you will see or what you're seeing in the physical world. Problem with all that is there's many different interpretations depending on what it is that you're trying to do, what life cycle phase you are in the program, and more specifically also what level of hierarchy you are in the system. And so there's as recently as 2022, the percentage of programs inside the Department of War was fairly small in really leveraging digital twins. A lot of fragmented interpretations of what digital twins are and how they would be used. And that's created some obstacles and some confusion. But as I said, we're starting to overcome that, at least for electronics. And so here I've got a picture that illustrates a little bit of what I talked about in that last chart. When you look at a purely hardware-focused picture of a system, on the far left is a chip, and on the far right is the mission modeling that we oftentimes do, the operations analysis of what different different laydowns of warfighting force, red versus blue, that type of thing. And the issue, and as I said earlier, we're trying to do a integrated set of models that starts from the chip all the way up to the mission. The problem we have today, and probably forever, is if we tried to model everything at the chip level at a very high fidelity, we couldn't actually do the mission modeling. We wouldn't have enough compute power. And so what tends to happen as we move from the left to the right is we can model things at the physics level below the chip and up to the chip, and then package, board, in a box, and then system of systems. And over to the mission is the models get more abstracted. We have to use the right fidelity for the right level of modeling. So at the mission level, we may not model the chip at a very high fidelity, but we model its effects on the board and then the system. And going the opposite direction, if we start with the mission, it imposes different contexts, different constraints, different requirements that we have to impose eventually down to the chip level. As an example, the bottom picture in the mission side, we have space environment, right? So we have to deal with radiation effects, thermal cycling, vacuum. Those effects have to be modeled as constraints as we move down to the left. And so different models with different fidelity need to be constructed to really integrate and create a full digital twin of a system. And again, different chip design will basically mean a very more detailed model. Chips then go into packages, which then go into boards, more abstraction as we go from left to right. So I'm going to get into a digital twinning for electronics. And before I talk about that, One of the key things to note, there's a great deal of commercial data out there that shows that hardware, the digital electronics, cannot really be separated easily from the software from a cost and schedule perspective. Over half the cost and schedule for developing an electronic chip is really related to test, verification, validation, and software infrastructure development. So I'm not talking about the algorithms and the coding of the applications algorithms, but the basic things like operating systems. So with that, when we historically, what's happened inside the DoD is we've had programs of record that will, and I'm talking now about the top right side of this picture. We would typically build something in hardware, test it, test it in a hardware in the loop type setup, and then find that it fails for some reason. We would then go back and fix it, and then test it and fly it again, and so forth. Oftentimes, the programs would go through 5, 6, 7, sometimes 8 trips through this cycle. And each time, as they send a chip out for fabrication, that would oftentimes take 9 up to 18 months, depending on the foundry. So that build, test, fly, rebuild, test, fly, meant many, many trips to the foundry or many spins. Very slow process, very expensive, and it's actually drove design decisions because it would take so long. Oftentimes, instead of developing a custom integrated circuit that was programmable, the programs would typically use an FPGA. And so what's possible today, one of the first things that NVIDIA did as a startup company was to go to digital twinning. And so there are tools now out there that will do what's called cycle accurate emulation. What that means is those spins you see up at the top right of the picture can now be done virtually in emulators. These are big, very large supercomputers that can construct a digital twin of a digital electronics circuit and emulate it so accurately that it basically predicts the manufactured outcome with very high fidelity. So for digital electronics, typically less than 1% error is what we've seen, what NVIDIA saw. Now, NVIDIA now has been doing this for the past 8-10 years. So every single GPU release out of NVIDIA has been a first pass success, meaning they go to the foundry to manufacture once, and that is the production run. It's because they can test, verify, and validate the hardware in the emulator. But as you see on the bottom right side of the slide, they not only do that, they're able to install an operating system, hypervisors, and a certain amount of software and test it all concurrently. So they're able to co-develop the hardware and the software at the same time, as opposed to historical practice of build, test, fly. They would actually do hardware and software sequentially. So these best practices are consistently practiced down the commercial sector. It's not just NVIDIA, it's Apple, it's Google uses these tools for their own chips. It's NVIDIA, obviously, and Qualcomm and AMD and so forth. Come on, why is this? So I'm going to talk a little bit more about validation and verification. As I said earlier, validation and verification consumes a majority of the cost of developing a chip, along with the software. And so what historical practice inside of the Department of War has been to use a single technique, the hardware software code, a single technique, basically hardware in the loop type testing. And I'll talk about that in a second. And each of the grids you see here on this picture is meant to represent the internal state that's been covered in a sequence of steps. So What the commercial sector does is a combination of different techniques. So the static methods that you see in the middle at the top is formal methods. So mathematically proving the software is correct. From a practical perspective, you can only do a certain amount of code or design. That's why you see, but get very tight coverage. And other techniques give you different coverage patterns. And the key thing is it evaluates the design from different viewpoints and handles very complex interactions depending on which technique you use. And so while it is impossible from a practical perspective to get 100% state space coverage, what you see today in the commercial sector is 70% or better. At least one major company, before they release their products, get well above 95% state space coverage. Hardware in the loop testing tends to give us 20-25% after several years of testing. So big difference in the quality of coverage. And I'm going to go to the next chart here. It talks about what I meant by internal state coverage. So field programmable gate arrays with about 1 million gates, after it's been programmed, has about 100,000 bits of internal state. So that means you have to check 2 to the 100,000 possible states, the very, very large number. Classical traditional hardware in the loop testing on the left here has limited visibility, because if you take a physical chip and you have maybe 1 to 400 wires coming out of that chip, it's very difficult to test everything or generate those internal states just through up to 400 signals. You can't really inject faults into the middle of the chip because you have access to the peripheries of the chip. And every time one wants to, at least with an FPGA, the similar process applies to what's called an ASIC, a pure silicon design. The probes that you can use, those 400 signals, requires either an ASIC respin or an FPGA recompile, which takes hours. And whereas on the right side, inside of the more modern emulators, there's multiple companies that have these. We have enhanced visibility because you can observe the internal states or signals of the actual chip that's under test. And so it's possible to create faults that are very difficult and dangerous in the physical world to generate. And the probes and the tests can be changed without recompilation. And that can be done in minutes as opposed to hours. And in addition to that, many of the tests can be separated. Thermal can be separated from power and so forth. And so that is actually internal state coverage. I'll say many programs believe that since they're testing 100% of the lines of code in a piece of software, that gives them internal state coverage, and that actually doesn't. Each line of software, the way it executes, will be highly dependent on the state of the machine and the software code and the registers before you enter that line of code. And so internal state is very different than lines of code coverage. And so all those techniques were examples that I just talked about of commercial best practice use of commercial tools. And as I referred to earlier, we had a number of Category 1 programs that the laboratory has worked directly with those programs of record. And so I'm going to just go through a few of these, starting at the top. You notice the life cycle phase of one of them was a modernization. It was an independent verification and validation of an FPGA that was deemed ready for flight tests. I'm going to talk in detail about that in the next chart. But the key point here is that many of our contractors and government partners had missed the defects. And what we were able to accomplish with the amount of money invested in the in IV&V that we did was we got a 20x return on investment for those dollars. So saved the program time and money. We had a similar effort on a large program of record where the contractor had proposed replacing copper cabling with fiber. And the estimate was very large, in the hundreds of millions of dollars. And digital twinning allowed us to show that we could use the existing copper cable and meet all of our future requirements without going to fiber. And so there, the return on investment was 30x or better. We had a third program that had a legacy card or a board, and that board had 50 obsolete parts. So either the vendors had disappeared from the market or simply weren't supplying those parts anymore. And we were able to, through digital twinning, create a digital twin of the original board, and then we're able to create a new design in the digital twinning space. We were able to show that the old design and the new design were functionally and performance-wise equivalent. The board now is been fabricated. It is now going through testing and certification. And so, and all of these, we're able to show that the software was actually able to run reliably on that new hardware as well. All right, let's move on. So as I promised, with the IVNV pilot, what happened was we had a defense contractor that submitted a design where they'd modernized their FPGA, the design within the FPGA, the code. And they declared it after several years of testing to be ready for flight test. And the normal process would have been to do some inspection, integration, and then go to flight test, and then fix and fly again. What the program manager did in this case was introduce a new process where we utilize these commercial tools that I've talked about. And basically where we receive the technical data package, this is the IP and the detailed design, and we're able to independently verify the design. So within 1 month, the independent team that the government had established, our lab plus a commercial partner, uncovered 8 severe flaws, 8 Dalby critical, actually. What that means is it posed significant risk to either life or aircraft. And then so that actually allowed our program manager to say, no, we're not going to flight test right away. We're going to go back and redesign this and fix it. In this case, it was a big opportunity. We were able to work with that defense contractor, teach them the new tools, and actually fix those 8 critical flaws in less than a month. So a total of 2 months to discover and fix, much faster than the 2 years that had been spent before. So that allowed us to significantly avoid a lot of issues during flight. All right, so in order to do all of that, we had to, hold on a sec, the charts I think have disappeared from my, let's start this again. All right, we had to establish digital twinning infrastructure for that electronics. So had to do that infrastructure had to do several things. One is basically model the function as well as the performance for that digital electronics. That meant decomposing the architecture down into the pieces that were involved and then doing the integration inside the virtual space. We had to model the data movement, the storage, and the processing. And then really looking at, between the different modules, interface design, and not just between the hardware pieces, but between the software and hardware together. It actually allows us to do security and safety certification, which is a major issue for things like dual mission platforms that have to go nuclear, possibly. The requirements for certification are much more stringent. We had to be able to do multi-physics simulations. So as I said earlier, many of our components have to operate in harsh environments, much like space or underwater or even on the surface. And so part of that multi-physics evaluation is basically simulating the power and voltage within a chip and on a board, make sure the signals have high integrity, they don't crosstalk, basically be able to simulate how the parts will operate in different thermal environments, as well as electromagnetics, and then the interactions between those different physics simulations. And so this environment has been used for multiple years now. It's been authorized to operate at, I believe it's impact level 5, which is unclassified systems, all the way up through ITAR and national security systems. And so that's available DoD-wide. A key thing to note, I'm talking about the F-35 program, this is a chart from theirs that's been released publicly, is they view the impacts of digital twinning as something that will reduce cost and schedule as well as risk. And so if you see the top, as well as program visibility, you see the top part of this picture, that's the classic picture where the contractor develops a hardware prototype and then goes straight to physical hardware in the loop testing. Whereas on the bottom, we're able to work our way up where the government works with the supplier and integrates things into a, if you remember the picture I mentioned earlier about the hierarchical model. So going to board, box, and then even at some point, system of systems type of modeling. So integrating those, and we've got in both of these, the cost and schedule impact of discovering errors at different phases of the life cycle. So you can think of going from left to right portions of the life cycle. And so the idea is that we can lower cost and schedule significantly. So much of the results I showed you earlier, those different programs of record pilot tests, led the F-35 program to invest in upgrading the capabilities we've got in that infrastructure. And so right now, the plans are to introduce hardware digital twins at multiple levels of the aircraft design, and obviously apply commercial best practice while doing that, and verify those pieces that really need very, very detailed certification. And with that, we're starting to see the results on the program of record of reduced development and sustainment cost, and rapid system updates from the industrial base as the industrial base learns how to do this. So that brings us back to this picture that I started with. So our playbook here is to rapidly move these digital twinning capabilities as we learn on the research side on the left, as well as from the programs of record. And we sort of mutually learn from each other. And so there's a committed now government effort to do these types of things, at least for electronics, and work our way up into full aircraft level simulations. So I'm going to end here, and that should give us plenty of time for questions and answers.
Thank you, Yadu, very much. Thank you very much for your presentation at this stage of the game. And I do have some questions now for you. I'm going to go ahead and blank myself out, so basically it's just the questions. Grant Epling from Lockheed Martin has asked, can you share any more details on the sustainment DRFM hardware digital twin that was shown in slide 8?
Let me go back to slide 8 and see which specific we talking about the parts obsolescence?
But he says the sustainment DRFM hardware digital twin. Otherwise, can you share more details on the sustainment?
Let's see. Oh, yeah. That's I did not talk about that. So that one I couldn't talk about too much, but basically in electronic warfare systems, um, there's a component, basically it's radio frequency memory, and we did create a digital twin of that, of the FPGA code that was involved. And I have to be a little careful because given that this is a distribution A audience, we could probably talk about that offline in the right setting, but that was a classified effort. But I think we're starting to see both cost and schedule benefits there as well.
Thank you. Manish Vaidya of Tata Consultancy Services asked, is there any consideration for circular materials, otherwise recovery in strategic areas, in such programs?
In terms of, I'm trying to interpret what the question is. Circular materials meaning recovery of old parts and then recycling them? Is that?
That may be your recovery in strategic areas. I would believe that would probably be the consideration in this question.
Yeah, so I believe programs are looking at that, but as parts go obsolete or fail, one of the things we have to balance. I once worked at Lockheed in one of the missile programs there for missile defense, and was it was the Trident missile system. Many of the parts had started to go out, not just obsolete, but they started to fail. And so they got into life extension where either we basically have to modernize, and so replace the old parts with new parts. I'm not sure the work I've done with the lab has looked at recycling old materials at this point, but I know there are people that are trying to do that.
Thank you. You apparently hit it because Manish said yes.
Yeah.
You interpreted correctly. Ikram Qureshi from Leidos has asked, how does the program keep track of supply chain risk management, including the obsolescence?
That is a difficult question to ask today. That is one of the challenges. We've got different organizations inside the Department of War that track parts, and so I can't say that inventory tracking is good as we'd like. It's certainly something we're working towards. That's a big opportunity. One of the advantages of digital twinning, like I've talked about, is we could eventually, with the right repository, be able to track the parts, assuming you have a real-time collection, right? And track those parts in a database that actually correlates with the actual design, assuming the IP has been acquired properly. So that's probably the best answer I can give you.
That's good. I have a question for you too. It's kind of a holistic issue here. With digital twinning, digital engineering, and all that is going around, considering 5097 JADC2, how is that being managed right now? There's certain barriers right now, still objective barriers to adoption. We go through all of the different government and the compliance issues, privacy and so on like this. How is this managed throughout the Department of War with the thousands of vendors that are out there today that are struggling right now under a direction with CMMC, FedRAMP, and others that are trying to go ahead and bring them back in with the industrial community itself. Does that make sense as far as the question goes?
It's multiple questions, right?
There is.
And so when you're looking at JADC2 versus digital twinning, there's an element of digital twinning involved with JADC2, right? Much of that will occur, much of the questions related to CJADC2 really occur at the mission level and then work their way down. Digital twinning of things like electronics or boxes sort of become overcome by the mission level issues. At the same time, many of the models that I've seen are because of the fidelity issues, may not actually implement the right fidelity at the communication systems, right? Connecting command and control together across the services, across geographies, across systems, really means that not only are we concerned about modeling the mission impacts, but the impacts of, let's say, not being able to communicate, the impacts of where you distribute the computation, how that distributed computation interacts. In early kind of analyses of the JADC2 problem, many of the engineers focused on a CONOP where they would centralize all computing, and therefore communications would be perfect. I think there's a realization now where and that communications may not be perfect all the time, and computation may need to be distributed, meaning command and control functions might need to be distributed and delegated. And so those are all sort of the high-level CONOPS and mission level things that you have to worry about, driven by effects out in the battlefield that are more related to electronic warfare, jamming, communications, and so forth. So that drives mission level effects. And that's without even talking about the impact of the electronics or the circuitry. And so many of those issues that give rise, I mean, you see it in Ukraine today, where they started off with drones, fighting drones, mostly drones fighting electronic warfare, but both the Russians and the Ukrainians now use fiber optic cables, very long fiber optic cables, to be able to communicate, at 40 kilometers or more. And so, very complex question. The digital twinning pieces, you have to look at, gets back to that integrated set of models. Those need to be applied. And so I'd say that's probably, I've kind of rambled a little bit about digital twinning and JADC2, but hopefully that answered your question.
That works. Thank you very much. Andy Kuhn from Lockheed Martin, one of your old haunts there, asked the question, in the context of independent V&Vs, that goes to slide 6, are achieved results from this methodology being captured for artificial intelligence processing for continuing optimization?
One of the interesting things in the electronics world is there's been a great deal of AI that's been developed that will help design circuits. When I've asked industry, the commercial sector, about automatically testing or generating test scripts, we haven't seen as strong a response. And so I'm pretty sure there's people working on it. One of the results we've gotten is for nuclear safety verification and validation. One of the programs we work with was required to certify their certain systems. And so we've been able to apply the more emulation-based testing to show how you could do nuclear safety certification faster and better. And that's resulted in changes to the Air Force manuals on basically how to do nuclear safety certification. So we're actually changing a certain amount of policy guidance and practice through what we've learned so far.
Excellent. Thank you very much. Very much appreciated, Yadu, all the work that you put into this and the direction you've given us for this. That will probably go forward to, again, your presentation and your comments will be available here very shortly on the DTC website, but thank you very much. And we'll conclude that and go on to the next one. Thank you very much, Yadu.
Thank you.
We're opening it up for our panel, headed up by Antonios, and we have 30 minutes on this panel in order to be able to keep pace and cadence. It's all yours, Antonios. Thank you.
Thank you, David. I'm very pleased to have a distinguished set of panelists for this particular panel focusing on the future of digital engineering with a defense, let's say, focus, but we can extend it more. Our panelists are here, Eman, Dan, Ian, and Adam. Thank you for doing this. And without further ado, I would like to jump into the topic of a discussion of shaping the future of digital engineering by asking the first question. Any of you in any order, it doesn't matter how we do this. If this engineering is an enabler, as we always say, and previous speakers actually have pointed this out, what is that we're enabling exactly, in your opinion, and especially in this contested environment that we are in, that we also hear in the news every day? Anyone?
So I'll start. So for me, digital engineering enables the ability to sense and make sense and act faster on decisions. So if it doesn't change a decision, it hasn't created a value. And digital engineering, in a sense, it should be enabling decision advantage in a time compressed and a high uncertainty environment. So today we're challenged with lack of data. We're not challenged with lack of data or models. We're just not able to make faster decisions based on that with higher confidence across different domains.
Very nice. I agree with you. Any of our panelists want a second and state their opinion about the same topic?
Yeah, I think in this threat environment we're faced, digital engineering enables systems can be designed, tested, and even fielded before we can see adversaries trying to respond to these. So again, in that threat environment context, we look at this as a way to build these and have better mission readiness through using digital twins. We heard a great example this morning with the F-35 and what they're doing through the virtual testing, the capabilities, and then that whole integrated approach through the life cycle is even enabling lower cost and scheduling reduction.
So I'll build on that a bit. In the electronic space, in particular, the states that the systems can get into are incalculable. Well, they're calculable, but they're unrealistic. So a digital element that has a million storage bits or values can have 2 to the 1 million states, and our electronic systems can have hundreds of millions, billions of those storage elements. So the ability for us to just say digital engineering is tools and process to get through is part of it. What we're looking for are the metrics, the data, the awareness coming from those systems so that we can make the decisions. The information that the digital engineering processes will provide to the team is going to provide an insight that we don't typically have today, certainly not in defense. Commercial does a bit more of it, but there's more that can be done.
And it's also about risk mitigation. You're reducing the risk by being able to understand it in the context of the modeling and the simulation, the environment, the physics-based approach.
Yeah, and I'll just say real quick, I mean, from the civilian side, it adds efficiencies that affect the bottom line in really important ways in order for these products to really make it to market. It reduces errors so that we're not finding them in the market, and it enables agility. And in context of these contested environments, like the ComNav surveillance problems, they're so complex. We need to be able to organize the problem space digitally just to tackle them.
Very nice. I think we covered this very nice, and we gave examples for multiple perspectives. The second question I have has to do with the following. I said here that we see excellence, Dan, in the Digital Consortium, we see excellence of digital engineering, whether it has to do with AI or agentic AI or data structures, or the way we can apply this into cyber-physical systems and physical AI. What prevents, in your opinion, successes from scaling across different programs and services? Is there an obstacle you feel that maybe legacy, maybe other factors create essentially those adoption issues that perhaps are coming the way? Maybe Ian, since you're working with a large organization for aerospace, so to start with you perhaps, because you might have some experience to share about this particular.
Yeah, for sure. I mean, I think it's culture is the starting point. This is it is a fundamentally new way of doing things, and it needs to apply, across the life cycle, which means from the top of the organization to the bottom of the organization. So culture is critical. And we also are still in a lot of places, I would say, including even parts of NASA, figuring out how this actually works, right? Because just to throw a model at something doesn't help. It actually makes things harder to read. So how are we really using these tools to solve the problem remains a little bit open.
Exactly. And then if I add you, Adam, now, because of your background in manufacturing and producing systems for OEMs or for the government or other organizations, how do you see essentially the industry side of things overcoming some of this obstacles, perhaps, to scale?
Yeah, so there, I'm going to break it into two communities in the commercial space. There's mission critical applications, industrial, automotive, medical. So in those spaces, the driving force is indemnification. So they're going to do this because they have to from a financial perspective.
Exactly.
We see a little bit less of it in some of the commercial spaces where commercial has enormously high volume. The risk of a mistake, like a cell phone, is so high that they're driven to do it. But if, in the absence of those two in commercial, it still comes down to financial choice. That's primarily what we see in driving it, but generally it's moving forward. In defense, the difference that we see there is how the programs are set up and contracted. If digital engineering was not part of an existing capability, it's hard to bid it into something new, and we get this vicious circle. I'll pause there because we can continue for the next half hour on that one.
I like this. And then, Eman, I know from your experience, you have seen cases of culture and mindset that I think Ian mentioned. So I'd like a comment from you on this as well.
Yeah, so from my view, scaling these problems is not a technical problem, it's an organizational one.
Exactly.
So these pockets of excellence, they don't scale because they're often built in isolated successes and not part of a whole operating model. So in one case, to give an example, there was an effective digital twin that was built to improve planning and risk visibility, but it remained confined to that one program that was built for. And when we looked closer, the data, the structures, the governance, and the incentives weren't aligned with the broader organization. So what prevents scaling is fragmented data ownership, lack of life cycle continuity, and incentives for delivery within these silos across the program and across the organization. So it's multiple things at the same time, and it's not a technical problem to solve.
Because I knew you were going to say this, the question 3 is ranked accordingly, Emma. And I say here, how do we avoid, we have essentially a vendor. I mean, Cadence is producing parts that you sell, right, Adam? You have obviously your own stakeholder here, but how do we avoid ourselves from looking into specific vendor tools while still preventing allowing the framework of engineering to essentially thrive within a context, let's say a semiconductor business that you are, Adam, or in general, whatever defense might be. But essentially, what do you think is the things we can do to become vendor agnostic or tool agnostic and more specific to capabilities, if you like, that essentially will enable this engineering?
Yeah, so it's interesting question for us. We don't do as much manufacturing. We do build our own supercomputer as part of our product portfolio. But in our work with defense teams, it's a very careful line. If we come in as a tools provider, we will so narrowly set the discussion that we actually reduce the likelihood that the defense community will pick up on the methodologies and standards and such that we're trying to pull forward. So our positioning, we've done training, we've provided electronic design automation training for some 2,000 to 4,000 program managers in the government. And the only way we can succeed with that is to make that information neutral. Now, that may mean that my competitors get a leg up because we've now created people ready to receive their information and their product pitches. But if we're going to move everyone forward, we have to float the boats. We have to pull everyone forward. So I think it's on individuals in the community to position ourselves to drive methodology over product, and the products will come. The people we talk to will know who we are. That's not a concern.
Dan, I want to pick your brain on Adam's points here regarding tools and vendors versus advancements. You see in DTC a lot of these things. You see tools, right? You see a lot of people coming in with essential solutions. How do we move forward the needle when it comes to the science, the technology, the advance of this engineering, in your opinion, through DTC, let's say?
Yeah, I think from that perspective, if you think about how we've approached, where you start your digital twin journey effectively, and that's through different frameworks, right? With the capabilities framework, looking at it in terms of understanding that, and that's all open source. And that's another aspect of this, is we do move a lot of the work product that we have and developed through our members in the consortium into our open source collaboration community. And we've seen that adoption pick up across many, many different areas, and we see that continued. And so that whole approach is really about bringing forward, and this is sort of the mantra with the Digital Twin Consortium, is bringing forward the innovators through that collaboration to demonstrate that thought leadership and make that available in terms of these these frameworks that can be adopted in that context.
And then, Ian, I'll pick again on you because of your involvement with FAA. Was you start a journey of this engineering with a stakeholder that has resources, but is also new in the area of transforming? How do you go about navigating the sea of tools and vendors to select what makes sense for you, essentially?
It's a problem, I'll be honest. Like, I wish I had the answer to this question. I would say that I don't know what the technical answer is. I do know that, the answer that Adam provided is absolutely the starting point, right? Like, we have to understand that the goal collectively is to float all boats, because the problems that we're facing, we're trying to knock down stovepipes. So if we have to choose the least painful stovepipe, like that's not gonna work for us.
So, Eman, I'll start with you now. So, as I say in question 4, we have several frameworks suggested within this engineering. And many of them, not necessarily have to have AI, but many of them, as you know, they truly support AI or integration of AI, or they're based on AI to bring autonomy. Are we doing this? Or what we do is retrofitting legacy systems with some sort of an AI patch. So we don't change the logic perhaps much, but we just add automation or some speed, and therefore we talk about this engineering there. So what's your opinion? What have you seen, again, from a technical perspective in the different examples of consultancy you've been involved?
So in many cases, we are still retrofitting legacy processes onto systems that are not expected how they behave. So AI systems don't behave that way. They evolve with data and with context. So traditional digital engineering frameworks were designed for deterministic systems where behavior is predictable and validation is done upfront. But the mismatch shows up when we try to apply static validation approaches to dynamic systems with AI. So, for example, like approving a model once at deployment doesn't account for how it performs over time under changing conditions. So frameworks today need to shift and be more flexible from one-time validation to continuous assurance, and where performance and confidence and risk are monitored over time. And that's where I like to anchor it to decision-making in context of operations and mission-critical activities, understanding those decisions, and then develop that life cycle framework from there, not the other way around.
And then, Adam, I'll go back to you now, because, again, you also create things, not manufacture perhaps. Are those truly meant to support AI and autonomy, or they just are good enough to also run AI and autonomy, and therefore they work, but essentially they don't change the paradigm of how they are supposed to work in a complex system environment, essentially?
Yeah, and I'm gonna pick it up on 2 quick directions that are connected. So I had the opportunity to sit in on a panel with requirements procurement experts from NDIA. And two of the panelists said that AI is going to fix everything in requirements and it's going to be super awesome. And my response was, no, that's not true. And the main point with that is, while you may have generative, I'll pick up on Eman's point, the generative AI can produce a set of requirements based on existing knowledge.
Yes.
Particularly in defense, we're trying to push the envelope in certain areas, and then we're trying to not push the envelope in other areas that we could procure at a lower cost to develop these complex systems quickly. So we need the connection down through the implementation flows to qualify. And so it's more an agentic flow, it's a connected flow, and the individuals throughout that process need to be aware of the modernized digital engineering systems. They can't just expect that AI is going to fill in that knowledge without those individuals being able to qualify it.
Exactly. Any comments from Stan?
Yeah, just one of the comments is, these frameworks can help with scaling, and we've seen that in terms of, we had released the AI capabilities framework,
right?
Also, in that context, but we really wanted to first identify what is a true, in this case, an agent, and what are those capabilities? What are those increased levels of autonomous operation? So many of these frameworks can be optimized for these AI applications, but they're not truly autonomous systems.
Exactly.
Right. And we've seen that in that context. That's why we also just released a couple months ago was the manifesto. How do I trust those agents, right? Those AI living in the digital space. How do I trust that there are no unintended consequences when they are in a production deployment environment? And that's where we had released that the AI trustworthy manifesto, right? Identifying those, really the foundation in terms of the governance and the safety for allowing that. So you really need to look at that in that entire perspective.
I agree. If there's no any other comment on this topic, which is very keen.
I would add just like real quick. I don't think we're as bad as retrofitting legacy processes, but we're not there yet, especially where the real bang for the buck is in critical systems. Formal verification is super important, and we're still struggling with the semantic problem. So there's some fundamental things for us to get over.
Very nice. Which again, this brings now to the point of if AI is in the loop, let's say, and we do this AI enabling systems. Eman, you have a title of AI enabled digital twins in your spiel there. Who owns this? Because that becomes complex, right? It's a complex system environment. A chip, a tool, a process is embedded in another system, is made by an OEM, is monitored by FAA, let's say in your case, Ian. Who is it? The program office, the engineer, the operator, a policy. Who then own that trust and that ecosystem to be able to make changes according to what the system in autonomous manner now then is operating with? Because again, that becomes an issue of like maintenance of these systems once they fully become autonomous, right? Eman, what do you think?
Absolutely, and that's where things get exciting when we talk about trust, right? Trust isn't owned by a single entity and it's distributed across systems, but it needs to be governed. That's when we talk about a lot about governance. But then in practice, engineers build the model, the program office deploys it, the operators in the field rely on it, and then the policy defines the boundaries of these models. The gap here, that all of these elements are often disconnected. So what's needed is a governance model where trust is tied to decisions, and that's where I keep talking about decisions, where decision architecture, like what decisions can be automated, where human oversight is required, what are the confidence thresholds for each decision, and where they need to be met, especially in mission critical environments. So instead of asking of who owns that trust, we should be asking who is how is trust operationalized across these different decisions that are involved in the governance model? So it's a different way of looking at it.
So Dan, I want to pick your brain now, and I want to ask you, since you're working with medicine, and we're talking about the virtual, the global virtual human virtual twin alliance, can you see parallels on a highly regulated industry like the medical industry with therapeutics and of course health being related now to defense processes in terms of this trust issue that Eman talked about ownership and about propagation or building it, if you like, as part of the system requirements?
Yeah, I think if you look at it from that highly regulated environment, right, the policy is going to set those guardrails, right? And we also heard yesterday where they were stating, you have the human in the loop, you have the human on the loop, multiple scenarios. Again, as was being brought out, accountability does need to be explicit. And we heard the engineer has to be involved in that sign-off. It can't just happen, right, autonomously. And that's where, again, you get that governance side of things. You understand what is required to conform to ensure you have that governance infrastructure, and then what evidence is required. And again, that goes back to the AI Trustworthy Manifesto, identifying all those different areas. So I think you need to look at it in its totality, but you cannot take the human out of the loop.
Exactly. All right. Unless we have some more comments from you, Ian, and I don't want to proceed to the next question. We hope to cover a few, but please go ahead if you have
Well, I just want to say that I think this is one of the most important questions, and I have yet to see the forum set up for us to debate the really difficult question around, is it the human or is it the machine? And like, I have a starting position. I'd love to be argued off of it, but this is super important.
All right. So the question 6 that goes deeper into this particular aspect. So if we have this risk that the engineer can actually pose to essentially work that is a status quo, what is perhaps, you think, a risk that modernization of these engineering practices, meaning a foundational change in the way things should be happening by policy, by governance, or by imposing rules, essentially based on what top-down rules might be from the Pentagon in this case. What do you think this poses as a risk to current big OEM legacy producing systems that essentially might be a risk that actually will cause resistance for some of this change?
So I have something to say on the OEM's role, and the value. I don't think digital engineering is eliminating OEM's value, but it does change where that value sits. So historically, value was tied to proprietary design and systems. With digital engineering, value shifts towards integration, lifecycle performance, and data-driven decision support. But OEMs that adapt by embracing open architecture and participating in a shared digital ecosystem can expand their role and change where that value sits in the ecosystem. And those that don't risk being constrained in this value generation, they have a narrow scope. So it's less about displacement of the value and more about that evolution that we see of the role of these different players inside the ecosystem.
The way I interpret this, Eman, is not about putting a threat on the OEM's existence. The way I see it is perhaps by putting a digital engineering framework, you might actually ask them to expose proprietary information, such as how data is collected or how data is reported. And that perhaps can have we've heard about distribution A or whatever classification levels there. Besides classification, cybersecurity might have some actual competitive advantage, let's say, disclosures that perhaps might be becoming a risk. So do you think indeed by enabling AI, including autonomous systems, including agentic, including bots that actually can work in the background of a system and actually learn, interrogate, query, whatever it might be, that might be an issue for some OEM to open up, if you like, their platforms, their systems in terms of how they can share information?
It is an issue right now, but that's again, that's the evolution part where they really have to, as you mentioned, the competitive advantage. They have to redesign where their value is instead of be treated as a threat of their business model. And I think that's where the lag is happening today.
Exactly. Exactly.
Yeah,
Comments
and
from
I'll lean into that a bit. If where we see resistance from some of the OEMs, I'm going to keep it very high level there today. And I think if the community looked at the business model differently, right? So rather than look at we need to build these systems over multiple years, and we're going to do cost plus improvements over them, and there's going to be physical field testing is the way that we anneal quality and capability into the systems. And we flip that to be a digital engineering process where we're turning at the rate that commercial does every year, 2 years. And we're folding in systems improvements, power, weight, size, mission profile. And we're on a cycle that's faster. The OEMs will grow. That's a business opportunity, but it requires a cultural change in how you view digital engineering. Do you view it as a business risk or a business opportunity? And until they cross over that, so I'll say it this way on the evolution: if we don't cross over to view it as an opportunity,
exactly.
there will be a set of new OEMs that will come up from an evolutionary perspective that replace. And
Exactly.
I don't mean to put a pallor on everything here, but this is an inflection, and we got to seize that opportunity to move forward.
Exactly. Exactly. Very nice. So we have about 3 minutes. So I would like to extend to their panelists the same question, but also have some parting thoughts so we can actually close this as best as we can. Ian, Dan, please give us an opinion, and then of course let's have a parting comment because we are 3 minutes to the end of the session.
I'll let you give your comment, Antonio. You deserve 3 minutes.
What I see, but is a lot of this discussion has been going on for a while in different sectors, but it depends on what hat you have. But I really want to hear from everybody here regarding what is really you think the biggest opportunity ahead. How can we achieve this? You feel what is it? Is it governance? Is it education? As we said, very nice, Adam. What is that we have to do first to make sure that we have a vehicle, essentially a guideline or a roadmap? I like the word roadmap for development. How will this in 10 years look like if we acted today? What is that we have to do, you think?
I'll chime in on that. I think the most important thing as we are talking about AI changing the world is we're starting to talk digital engineering, but I think we should start talking about value engineering, where what is, commenting on Adam's points about competitive advantage, the pricing model, our business model, our organizational change, culture, all of this requires us to go back to the basics and discover that value. So I'll call it value engineering.
Right. I like that. Ian and Adam, Dan?
I like what Eman said too. I mean, I just use different words to say the same thing. I think the most important thing that we could spend our energy on right now is with the people and the culture, and have this become the new normal, deliberately, not just organically.
Thank you. Adam, parting thoughts?
Yeah, so very brief. So maybe this is more of a I'm a New Yorker, Bostonian, East Coaster, so a little bit of bare knuckle. There's a combination of shaming and pedestal. For those that don't move forward, I think the shaming part's going to happen naturally. What we do in that is we put those that do lean forward, that do embrace digital engineering, put them on a pedestal, put them in the bright light. It's very hard for naysayers to talk from under the stairs, from in the dark, about how this can't work when someone is in the light. So let's put our collective partners that do lean forward into the light, and they'll lead us forward.
Exactly.
Yeah, I think we've got to continue to work to break down the silos that exist, and we've heard some great examples. I mean, digital engineering, we've seen the value that can provide and has provided and will continue to provide, but we need to figure out how to address that big interoperability question that's out there, and breaking down and opening up the sharing of the information. And also, as was pointed out early, make sure we're training the workforce of the future to addressing those skills gaps.
But it was a pleasure to have this panel, and I thank everybody here for contributing their valuable thoughts on this particular topic.
Thanks.
Thank Antonio, Dan,
Thank you all.
Ian, Eman, and Adam. Thank you very, very much for this outstanding work. So I'd like to introduce Chuck Brooks. He's been introduced once before. Chuck is going to be discussing and going forward with regards to his presentation on securing the AI digital engineering ecosystem. I'll turn the time over to Chuck. You've got it.
Thank you, David. It's a pleasure to be here to speak on an important topic. Great conference so far, and my talk is really going to be just more of the frameworks that were talked about earlier. The deep dives were done already, but I'm going to give you a refresher on some of the key elements that we need to know in our digital ecosystems, particularly as it relates to cybersecurity. And of course, there are a lot of them that were discussed, and hopefully my slides will provide you with some takeaways that you could use again. And so shall we begin right now?
You got it.
Okay, slides. Okay, slides. Great. So my talk is called Securing the AI Digital Engineering System. And let me get right to the second one here. And this is really what it's all about. We're entering a rapidly evolving fourth industrial era where the digital and physical worlds are now converging. And what's hard to deal with is the pace of this technological advancement we're experiencing. It's just so rapid that it's reshaping industries, it's reshaping government policies, and we're basically reactive right now because we're not sure exactly where it's going. And the reason for this is we weren't really expecting it to happen so soon. And I think primarily after COVID, we switched to a digital ecosystem, we communicate, and then it took off from there. And then, of course, I'll go into some of the reasons and technologies in the next slides. So, as I mentioned, technology is advancing, which means that both the opportunities and the challenges for security, particularly cybersecurity, advance with it. You're going to be seeing more sophisticated threats. You're going to have the ability to make rapid attacks, to automate them, etc. And so it's really evolving at an unprecedented pace. And the interconnectedness of everything is now increasing. So when everything increases, the threats are now connected too. There's a mesh. So there's a lot of new attack vectors, which means there's a lot of new risks. So what are the technologies impacting digital transformation? Well, there are quite a few. I highlight in this talk a couple of them, but of course, artificial intelligence has been, the main focus of conversation in this conference and pretty much everything in the news. And that's happening at a quick pace. Cloud computing has been there for a while. It itself was disruptive when it happened. But now you're even seeing from cloud computing things moving closer to the edge and devices. And of course, the Internet of Things, which has also been around, but the connectivity and the amount of devices is exponentially changed. There's hundreds of billions of devices now out there in the globe and trillions of sensors. And then another thing in the news recently has been quantum computing. Quantum computing was talked about a few years back as something distant, maybe 2040, 2050. But it's been revised drastically. Google came out with a statement a couple weeks ago, said that you need to prepare for being quantum, your algorithm's quantum resistant or quantum secure by the year 2030. So it's been moving up, and I'll get into a deeper dive on quantum too. Blockchain technology, which has been around again, it's really more of a ledger system, but it's important for cybersecurity. And of course, the big data and analytics, which is really what what artificial intelligence enables in a bigger way is something where you can use the data and synthesize it and put it to action. And then, of course, there's 5G, which is really the delivery system. There's a lot less latency nowadays because it's going faster and faster in speeds and capacity. And we're already working on 5G. So these are the quick overview of the technologies that we're talking about that are impacting the digital ecosystems. Now, I'm sure a lot of you recognize this picture here. This is HAL. This is HAL 2000, actually. And it was part of 2001: A Space Odyssey. And the interesting thing about HAL was that he had sentience. So he was able to make decisions. In this case, he was pretty nefarious, too, because he actually ended up disposing of an astronaut. But artificial intelligence isn't there yet. But it is based on some things that are really happening quickly. And this is really related to speech recognition, to learning, to planning, to problem solving. And I'll get more in detail on some of the components of AI. But AI is significantly moving at a rapid pace. So this is really a highlight of some of the things that you need to know, just an overview slide, and I'll leave all the slides so you could use them again, of what AI is impacting currently and will impact in the future. Of course, there's the automation issue, automation and efficiency. There's the data analytics. There's the interaction with other emerging technologies such as quantum. There's basically the rebuilding our business priorities. Now, how we structure our business, where risk management is all impacted by artificial intelligence. Modernization of industries also with that too. And of course, the work in the economy, huge issue as it's displacing people, but it may create, hopefully, other jobs in the future. And of course, what we'll get into in the big part of here is really the cybersecurity challenges, because AI is a tool. It's a technology. Every technology is a tool, and it's a tool that can be used for good and bad. So, to summarize, we really stand at the most consequential technological convergence in history. And I use that word because the convergence really is involving a lot of interesting aspects of technology. So what we're seeing now is AI is embedding into every layer of digital engineering. You talked about earlier in the conference, digital twins, and also model-based systems. We're seeing autonomous platforms, much more IoT-enabled infrastructures now. And what this promises is exponential innovation, predictive precision, and transformative efficiency. So with every leap in capability comes some dramatic expansion of vulnerability. And again, that's the two sides of the coin with cybersecurity. So we talked earlier about digital twin technology. I wanted to include this slide because I think it's a good visual of what it is and how it works. I think we just lost the slides. Let me see if I can go back to them. Okay. Hold on a second. There it goes. There it goes. Okay. Back to digital twin technologies. And so it's really creating a physical asset you can work with, a computer-aided design, or however you want to do it, and other controlling tools. But let me get into the meat of this. So what we're talking about with artificial intelligence is really a dual edge. It's a dual-edged sword. So it works as a shield, of course, for defense, because it can provide real-time anomaly detection. It could be used for predictive threat intelligence. It could provide behavioral analytics and autonomous responses, in SOAR. It can expand attack surfaces and digital twins and autonomous systems. It can be used to detect model poisoning and data exfiltration in any supply chain compromise. It works with updating legacy infrastructure, obviously automation, and could be used for helpfully detecting ransomware and DDoS attacks. It deals with human factors and recognizing phishing, insider threats particularly, and it also could alert you to weak AI governance. There are issues because it could have algorithmic bias, and there's issues also with quantum decryption risks right now that AI is not quite prepared for. So as a spear used by adversaries, they've been pretty good with already mobilizing some of these early automation technologies and phishing attacks, and also finding vulnerabilities. There's also types of malware. They're able to even more enhance polymorphic malware, where it actually changes form to avoid being detected, or can be used later to trigger by a biometric trigger. And so all those things are being enabled to the hackers. And of course, the most common thing talked about is the deep fakes, the social engineering. Now you can go to your social media, figure out where you shop, where you bank, who your family members are, where you work, and they can develop a social engineering profile and use that to create deep fakes to basically use mostly for ransomware. And this has been done significantly, actually, unfortunately, too well. Most of them are phishing attacks where they open on a fish, but there's actually been live deep fakes where money has been transferred, people imitating a treasury officer or someone from the C-suite. And that happened a couple of years ago in Taiwan. And so also, that you have something I'll go into more about is agentic AI, which is now attacking at machine speed. And it has more capabilities before than we had with generative AI, but I'll go into that. But the bottom line is technology is advancing faster than our policies, institutions, and our workforce readiness. And so we need to catch up. There are obviously some frameworks being developed both here and in Europe. And but they're sort of in a state of flux right now. Institutions are not unanimous on how to do that. There's not regulations that are concurrent, and workforce readiness is probably the worst part of it, as most of the workforce has no understanding of how to use AI and what are the risks to it. Next slide. So specifically, there are quite a few, and I touched on them a little bit, but here's a deeper dive. The uses of artificial intelligence in cybersecurity include threat detection, again, spam and phishing, malware identification, endpoint detection, spam filtering and bot identification, password protection, and user authentication, autonomous patching, which is really one of the areas where it's most readily used right now, because patching is a difficult task, particularly for a lot of SOCs, where you lose administrators, there's a lot of turnover, and there's just too many things to follow. Now with threat intelligence and patching, it's easier to do it when you automate it. And then there's other risks too, with adapting to predictive analytics and incident response. You have to really now have a framework and a plan for incident response, and AI can greatly enhance that. It can use experiences of others who have been breached and apply those incident response to, and basically customize them to your organization. So that there's good and bad again. So one of the areas, of course, is the analytics with AI. It can examine past data sets and find root causes of incidents, and look back at what indicators on the network activities were, which is really important, particularly if you're an analyst. And it's not just finding them and knowing what they are for the incident analysis. It's automatic updating of mitigation tools to prevent it from happening again. But also, if you're an analyst working in a SOC, or even if you're not in a SOC and you're a cybersecurity analyst, you were tasked with writing up briefs, reports that sometimes took days to write, and the analysis of discovery. And so now with AI, that can happen within minutes or hours. So it significantly enhances the capability to provide a reasonable and understandable analytics of what happened during a breach. So other uses, of course, and I mentioned this earlier, is insider threats. Insider threats is probably the second biggest challenge to cybersecurity, other than general phishing attacks, which are so common. Insider threats could be deliberate or accidental, and the deliberate ones have been very tough to find because you don't know who's doing what on your computers all the time. As administrators, lots of tasks. So, but with AI, you could recognize abnormal behavior or changes in behavior and flag something. So if there's someone that's actually exfiltrating data that shouldn't be to a different account, et cetera, AI can catch that. And then it also could significantly reduce the false positive, which are a real pain for anyone looking at any kind of cyber incident, and enhance access control. So those aspects of AI are also very important to understand, and especially insider threat. And I mentioned the deliberate, but a lot of them are accidental. So if you're the misconfigurations, or someone leaves something open an administrator when they leave for the weekend, AI could flag it. So AI does have a lot of different elements to enhancing cybersecurity. And so, of course, there's the other challenges that I mentioned. And this requires a lot more investment and capabilities to be able to deal with these advances. And there's so much out there that really I highly recommend managed services, because it's almost impossible for just a small office or medium-sized office or business to be able to deal with the changing threats with AI alone, and understand just the regular threats that you have with running a cybersecurity operation. So these challenges are just magnified with AI. So hackers, it's become a quick tool with hackers. And the dirty secret is not so much of a secret, is that cybersecurity is very asymmetrical in the benefits of hackers. They only have to get lucky once. They automate targets now with AI, to tens of thousands of potential targets rather than just do it manually. They can find vulnerabilities now very easily with AI. And a lot of these organized criminal groups, particularly overseas, have hired some of the best and brightest to help them, because they reap a lot of money, and they also share some of the money with their state sponsors. And about 85% of cybersecurity attacks are financially related. And so it's easy to see why it's become a criminal enterprise, and a lot of the brick and mortar crime is now morphed into digital crime. So it's a real issue, I think, to look at how we basically deal with this threat, because it also involves legal, it involves geopolitics, and it involves understanding a deep sort of intelligence dive on what the enemy or the adversary has in their tool chest. So again, a summary, and I won't go too much into this detail here, but because I think it's what stuff I've just mentioned, but it does, significantly help in advanced threat detection and advanced decision making, and dealing with issues at the edge, and real-time threat identification and analysis. And again, the challenges are pretty much what I just said, that you're dealing with a big universe of targets, and when a hacker could use polymorphic malware, or use automated phishing attacks with realistic graphics or deep fakes, it becomes very difficult to know, and everyone is being flooded. It's not just on emails, it's on SMS and other things too. So the reality is that AI has introduced a big component for cybersecurity, and we have to be able to understand it. And so, one of the final things is, I mentioned earlier that, it started out a few years ago with ChatGPT, and is soon become now agentic AI. And the difference really is that generative AI, you had to do the ear prompts. You had to do a huge amount of instruction to get anything done. Now with agentic AI, a lot of the hackers are creating their own agents. They go to the dark web, create these agents with tools, and they use them to mix in with phishing attacks, etc. So these agentic AI could overload a system. They could be used for bots. So there's a significant risk in agentic AI, and that's one of the things that cybersecurity is trying to confront right now. And so the next slide, which I'm getting into, is that, again, I mentioned that artificial intelligence is here and now. It's quickly advancing to all different types of capabilities and challenges and benefits and threats. So now what we have is an interesting thing with quantum technology, which is really could revolutionize everything because of the capabilities. And I won't get too much into the details of the physics of it, but it allows you quantum computers to do much more than any classical computer, like trillions of times faster and more capacity, and they can do things at once. Now, when you talk about quantum computing, everyone thinks of this big gateway computer like in this picture here, but it's more than that. There's photonic computers that are already out there. They're quantum. You have quantum sensing, which is already being used on GPS, and you have quantum algorithms. So quantum is already here. What they talk about when they talk about, in the next slide here, is Q-Day. And that's really when large-scale quantum computers, like when I just showed you, will be able to use a Shor's algorithm to break all public key systems, and including the RSA keys, et cetera, and all these things. So basically, all the stored data that has been stolen can be decrypted quickly. And also anything that's currently being breached or was breached recently could also be decrypted. It poses a big threat to security and national security. And Q-Day keeps being moved up, as I mentioned earlier in the talk. So the key now is it's required for everyone dealing with the Department of War to have quantum secure algorithms. I think by 2035, and they may have moved it up. But most companies right now are pursuing that. There's a lot of interesting technological approaches to that, from polymorphic encryption to asymmetrical encryption, to other ways too, which are pretty interesting, which are non-numerical. But anyway, cryptography is back. So these are, in summary, some of the big trends that I see coming this year and on, and a lot of them have already been here. What we have, of course, is the ransomware surge, and it's a surge in a different way because it's much more targeted. It's not that there's more of it, but they're able now to know, they know who has money to share it with their other adversaries or sell it, and it's being used because they pay in cryptocurrencies or digital currency or in cards. And so ransomware is surging in the amounts, not the numbers. So zero trust security, which was promoted a few years ago across government, now in industry. Of course, you have to know what is in your network, who's there, whether it's device or person who has administrative privileges. This was one of the problems we discovered with SolarWinds when we were hacked with that there's others, basically in the networks already we may not know about. So zero trust is a prudent policy, and it's continual. Work remote security, it's here to stay, mostly hybrid right now. But after COVID, we went to that pattern, and a lot of it's still there. AL and ML, as we just talked about, cloud security challenges. Again, there's a lot of people that use various clouds, hybrid clouds, and still want to keep their data on premise. IT and OT security. OT is an issue because, as we saw with some recent breaches, there's a mix. The Colonial Pipeline is a good example of this. OT legacy systems and IT are now coupled. So that introduces now a new level of risk, more vulnerability. And the problem is that they have different security protocols. And so, with the Colonial Pipeline, they had to cut everything off, stop, because they didn't know if it was the OT was infected. So it does something. It is a new area that we need, or not new, but it's an area that we need to apply more focus to. Cybersecurity regulations constantly changing. We have identity access management, which is a real key part now to AI. You have to really prove who you are now, because there's so many ways to fake identities, and who controls that. Of course, administratively is really important. Supply chain vulnerabilities, always the third parties, small companies were the target of a lot of industrial espionage, and we've tried to rectify that, particularly in government, but there's still very many supply chain vulnerabilities out there, and unfortunately, AI is good at identifying those too. Incident response and threat hunting, again, AI has enhanced that a lot. Privacy and data protection, it's an issue that is different here than it is in most of the world, particularly in Europe where they have GDPR. But a lot of us say that there's no such thing as privacy anymore. Anyway, but it is a balance, because there's a lot of commerce that's done through marketing of data that you've openly provided or inadvertently provided. And of course, the AI-powered cyber threats, which I mentioned. So just a quick overview again of the trends and strategies. Evolving threats require proactive strategies. Can't be reactive in this kind of environment anymore, which has been traditional with the bolt-on approach to cybersecurity. Ransomware as a service is now becoming more prevalent, as are other services too, with hackers as a service. Nation state and advanced threats are targeting critical infrastructure pretty regular now, testing us, particularly water and energy, transportation. Cloud misconfigurations can cause breaches, and we've found this out in some public companies over the last couple of years that lead to billions of dollars of stock loss. Insider threats still pose risks, although AI helps identify them better. Zero trust should be implemented everywhere in any approach. You need to adopt responsible and secure AI. It means you need to understand the limitations and the bias and the capabilities of what platforms you use. We must prepare for post-quantum cryptography, which is around the corner. You need to focus nowadays on resilience, recovery, and continuity, because no one is invulnerable to any kind of attack. And so the real thing is how quickly you get back up working, or do you have backup? If your data is not backed up, or your key data is not segmented, if you don't have the right policies in place and coordinating with your legal and public relations and your C-suite, and of course the IT shops, you could be in big trouble. So resilience and incident response, I think, is integral to anything nowadays. And then we need to invest in workforce training and education, because we're in a new era. And maybe computer science be overtaken by vibe computing, but cybersecurity hasn't, and engineering hasn't. And so there's a lot of science that we're behind on. We need to build out those capabilities again, and also see where AI takes us, and also prepare for quantum. So there are really 4 pillars to any strategic framework for this proactive resilience. Security by design, where you actually build things by design, combined with zero trust. You assume the breaches and you verify everything. You have to harness AI defensively for predictive analytics and human oversight and ethical guardrails. You need defense in depth, which is collaboration with your other vendors or your clients. You need post-quantum cryptography, and you have to really build on public-private partnerships, both at the state and federal levels. It's about people, culture, and governance, upskilling, AI literacy, leadership accountability, and we need to move from compliance to really strategic resilience, which is really the theme of this talk. So, in summary, again, the AI digital engineering system is here. The window of security is narrowing and closing. We need to work fast on this. We need to invest in the people, process, predictive technologies today. We need to prioritize data segmentation and encryption. We need to conduct regular AI simulation, red teaming, and we also need to have rigorously test digital twins. And we need to leverage managed security providers, which is really the only alternative I see now that the private sector has taken on a greater burden and everyone's become a target to really address some of these threats and provide mitigation. So, quick overview with the three key design defenses for cybersecurity. As I mentioned, security by design, defense in depth, which has been traditionally DoD, or now has changed a little bit, and zero trust, which I've talked about. And then, of course, the basics. People forget. Sometimes the easiest thing is not to make yourself lowest hanging fruit. And so there's cybersecurity hygiene. Where how you leave your computer, what your passwords are. Do you use multi-factor authentication? Do you have advanced firewalls, intrusion prevention, antivirus, anti-malware, anti-spam? Are you encrypted? What are your web application controls? What are the red team, blue team elements of your preparation? And do you have employee awareness training? And where you need to know how to patch, what data loss prevention basically you need to implement, what vulnerability scanning you need to do, what your security information management strategies look like. Do you model your files, and do air-gapped compatible solutions to keep infrastructure isolated and protected from other environments. And of course, as I mentioned, incident response. So again, there's a lot of elements there, because that means cybersecurity is not monolithic. There's a lot of levels of depth to it. And again, that's another reason why you need to bring in expertise. So essential principles then for navigating the technological and cybersecurity future where we're at: integrate emerging technologies securely using strategies and frameworks. Cybersecurity is everyone's responsibility from now on, from the leadership and the C-suite to end users. And protecting identities is critical now, and ensuring trust is also for any kind of digital transformation to succeed. So at this point, this is just a recap of my book that I put out, basically, how artificial intelligence, quantum, and 5G and IoT are impacting cybersecurity, which I wrote last year, which really already needs to be updated. That's how fast technology is moving. And this is where you can reach me if you need anything, but the easiest way is always on LinkedIn. Now I'll revert back to Dave for questions.
Hey, Chuck, thank you very much. Outstanding.
Thank you.
Let me just go ahead and come off here. Basically, there's several questions that actually spring forward. AI/ML has now created a whole new landscape right now for threat landscape for cybersecurity. As you mentioned, and it's very clear that the agentic AI is polymorphic, which basically begins to make the traditional kill chain just a little bit more challenging in order to be able to go ahead, both assess and protect. We've talked a lot about digital twins, interoperability, and utilizing digital twins in digital engineering. How does one protect, and how does one, what do you recommend when you have multiple different verticals and they're working with digital twin, beginning to amalgamate those digital twin packages together for interoperability? How should the designers of that and the management look towards protecting those digital twins from being assessed by by the threat actors? And again, that goes to harvesting a lot of the data and the essential materials in there, CUI, even classified information.
Yeah, well, that's a good question. I mean, there's a the easiest way is segment them from your data. That may be the targeted attack of hackers, because and the second part, of course, is have that encrypted. But the digital twins are essential, for the simulation activities, and they need to be continually updated, interactive, and that's where AI now also plays a role, because it is able to synthesize some of the findings of what digital twin simulation can provide for predictive analytics and also reactive. So you're right. I think it's really it's really become a sort of a crown jewel in itself. So just like you protect your finances separately and have them guarded with a variety of cybersecurity applications, and also backed up. I mean, I think you need to do that now with digital twins, because to adapt to this threat environment, you need to rehearse and you need to understand what threats are coming in, and the best way to do that is simulate it with a digital twin.
Good point. You wrote an article recently, which basically I think is an outstanding article. I read it through. Why cybersecurity strategies and frameworks must recalibrate in the age of AI and quantum threats. Do you want to kind of unpack some of the thoughts you had in that article?
Sure. No, I mean, it goes into a sort of the presentation. We've been late in coming to cybersecurity to begin with. We never built it for security, and it's really been a reactive, bolt on this endpoint, do this, add this antivirus, and they never really worked that well. There's still thousands of breaches every year that go up in cost and also in implication for companies going out of business. But what has happened now is that the environment has really changed so drastically that a lot of these initial frameworks were, how you deal with a cyber attack, what should be your response, your line of reporting, who should you coordinate it with, what tools do you need? All that stuff is really changed, and most of it's become obsolete. So you have to now have new frameworks and understand these frameworks, because that's where the threats are coming from. The most important part of any framework is dealing with mitigating threats or knowing what they're about. So you can't do that anymore with the old systems. And so you need to look at AI, particularly right now, and exactly what we talked about, mostly the agentic AI, but also the other aspects of it too, the automation part, the polymorphic changes. I think that needs to be integrated in every security framework, and you need to start preparing again with your frameworks too of cryptology, where you need to protect with the capabilities much greater, particularly when quantum comes on. But even when AI is here now, there's ways now that some of the encryption's already been broken, and there's even talk that some of the quantum lower end qubit computers are capable of breaching most of the keys already. So I think what you did in the past doesn't work anymore, and you need to prepare new. And the other thing is, I think with a lot of these frameworks were done really for IT shops, and I think one of the things of being resilient, it has to be holistic and company-wide. And yes, IT needs to be a key component of it, but the C-suite needs to be at the table. You need everybody, from your legal to your accounting to your PR to your sales and marketing too, because when you do deal with an incident, it can't be isolated, because you have to have a response, because a lot of the viability of business now is either on the stock market or with a reputation in the community. And when that happens, it could basically deeply threaten the survivability of a company. So I think frameworks need to be updated, for these new technologies, and look at we need to go beyond what is there now and look at also privacy as part of that. There's some parts of GDPR that make a lot of sense. I think depending upon what kind of industry you're in, what your threats are, your profile are, you can adapt these profiles, and still NIST provides some good general stuff, and so does MITRE. But I think you really need to look at, particularly with AI more than anything right now, is really just basically change the paradigm of cybersecurity, and these old ones are just obsolete.
Thank you very much. That's very, very well stated. I think that there's another question here, goes on to the education portion of it. We're producing ostensibly about between 26 to 30,000 cybersecurity professionals, and I put that in quotes, every year through universities, tech schools, and so on like this, and through, and I think that one of the problems that exists today, perhaps you can comment on this, are we really keeping up with what the adversaries are doing with regards to their education in cybersecurity? Number one. Number two is, how are we dealing with the antiquated systems that are out there today? I've been in the cyber business for almost several decades, and in a professional today. And I look at this I look at antiquated systems, not only IT functionality, but also the software systems out there today that are highly susceptible to advanced AI type of intrusions. So what are your thoughts, education and also the legacy systems that we're actually working with and practicing on?
Yeah, no, I think we have a real, we've tried to address this in the past. There's been a dearth of cybersecurity expertise. It's global, but particularly in the United States. And you mentioned earlier, are we doing enough in education? I think you have to look at, what the Chinese are doing and the capability they have now at younger ages in pulling people into that profession, training them mostly in science and technology and engineering. Our engineering and science is poor in this country. And it's not just for cybersecurity. We need to adapt our whole educational system to deal with the new realities of our technological future. And we're not doing that. And people are being left out now. They're finding out, well, I don't understand what's going on. AI is taking my job. But it's not that AI will take your job. It's needing to know how to use AI. It's needing how to do cybersecurity. What are the challenges now with cybersecurity? And I think there's a lot of online certificates that have popped up in that area, which are good. There's more education. And again, it's not all technical. I think a lot of that also is soft skills, to be able to communicate, be able to lead, and that's lacking too. So I think where I teach at Georgetown, they get a combination of that, but they have to go through a variety of courses, and they're at a graduate level. So, but already have had a few computer science undergrad majors that say their other fellow students are having trouble getting jobs. So. They pivoted. They're going to improve themselves by understanding more of the implications of technology and security and cyber, and specialize more. But I think we have to really have a wake up call, almost like a moonshot with the technology. Hopefully, the recent Artemis stuff to the moon and what's going on actually, and the precision. I think I got to commend the military for the kind of technological prowess they've had, particularly with the Air Force. Which has really been amazing with the use of smart weapons people. I think it's going to attract a lot of people to government and particularly the military because it's really so amazing, and it's not being talked about. But whether you're for or against the war, it doesn't matter. That the prowess of performance of these planes in precision bombing and intelligence integration, multi-domain warfare, robotics, etc., is really, when you look at government and you look at particularly the military, is very forward-looking. And this is a move. This is the world we're coming into with robotics, which are now popping up too. That's another area of things we need to understand. So, I think you sum it up. I mean, you have to prepare, and we're behind many countries. I mean, I think there's a lot of other countries that are focused, like India, in training people engineering. I know Israel identifies kids early on in their early grade school for science and technology careers in cybersecurity. And we need to do the same thing here. There's no reason why we can't. And I think our system's broken in a lot of ways educationally, but primarily because it's operating in an era that's 40 years ago. And we need to start there. And if we don't, we're going to find ourselves behind.
I think again, very, very, very well stated. I think we're in a real stage right now of marvelous opportunity. Of a matter of fact, exciting opportunity. You find major corporations, AWS and others now, that are reforming their entire environment around AI. What does that mean? I'm not sure that everybody really understands that yet. People are being discharged now in order to be able to make room for that, that new opportunity here at this point in time, and new modeling for these companies that are now removing themselves from the traditional and going into AI based functionality. But I think we're still at the problem, and perhaps you can comment on this thing. I think we're still in the position right now, not fully understanding what that really means. We rush into it, and not with them. And I think that we're trying to rush into AI in cybersecurity, trying to rush into business and opportunities there, and we're still learning what that really means. And I'm not sure that we're ahead of the game at this stage from the threat actors.
Yeah, no, I think so. I think you summed it up pretty good. I mean, there's a lot of movement, investment, but it's early stage. And but problem with businesses that want the latest shiny technology, they didn't have strategy behind it or understanding of the return on investment yet. I think that'll eventually happen. I think it's made, the platforms have really improved greatly over the last year. So I think they're coming to a functionality for efficiency and optimization in business now could be used by a lot of them. A lot of companies, a lot of universities now are adopting platforms of AI, but they have to also put the regulations around them, the use cases, and you want to also keep humans in the loop. And I think that's another problem, with people thinking that AI can do everything. It still has programmers that are biased. And so we need to have, and context is another issue. So you need to have a human in the loop. But I think you need, saying it is an opportunity for a lot of people to redirect their careers, to understand it. And again, the marketing of it and the sales are going to be soft skills there too. And how it fits into businesses. There would be people that have to go in there and do the planning and do the prompts of what you need. You have to have understanding as a business. You don't just plug in and say, give me AI. You say, what do I need AI for? And you have to have a strategy and a platform, a risk framework, everything put together beforehand. So, and then you use AI to really fine tune it. But, I think it is, that's what McKinsey's saying now too, that it's going to end up creating more jobs and taking away. But I think the quick rush was to, hire as many people they could, particularly programmers, to get, the competitive edge out there for investment by a lot of these companies. But I think that's sort of waning now. And I think you'll see in the next couple of years, particularly in other industries where medical advancements coming, the people are going to have developed expertise in how to use these devices, where the potentials are for health, other things, as well as, again, every other component of the industry you could think about has an AI touch to it somewhere.
Yeah, I think going forward too are 16 different critical infrastructures that are out there as defined. I think still each one of those still needs to go ahead and address the AI component within what they're doing. That goes to energy, telecommunications, everything else. And so I think that what you have staged here and unpacked greatly really influences all of that thought. And then going back to what we talked about before, how AI, we can protect that within the digital engineering community and that of digital twin community too. Thank you very much for that. Do you have any last comments there before we go ahead and close out?
No, I mean, I think it really, well, to summarize it again, I think it's, we have to be more resilient and focused on going forward than looking at the past. I think like you said, we have a new opportunity, and we need to really work together, because the threats for the moment are more sophisticated and more lethal than they were before. But there's opportunity to stop those and mitigate those too. I think this is really a wake-up call for a lot of the nation now, that business as usual is not business as usual anymore.
Right.
And so I think that with people like you have the expertise to share, and a lot of the others need to really continue this educational outreach to get us to work out understanding of what AI brings, what quantum brings, what everything else brings, and really it's really the mesh, and I say the convergence of a lot of these technologies that will really bring us great promise, but there are challenges.
Chuck, thank you very much. You met all expectations. We appreciate your presentation and all your comments, post presentation. Outstanding. Again, just to summarize for the audience here at this point in time, we're going to put all of this on our website, social media, once we were able to go ahead and synthesize all of the presentations that were made. Apologize again for the kerfuffle with regards to how, in fact, this was transmitted and the technology issues that we have, but we'll correct those next time around. This is not the last town hall we'll have. Thank you very much for your audience. Thank you very much for everyone. Thank Karen and team for all the quick reaction that they did in order to put us back online again. Appreciate that very much. We'll go ahead and close this thing out and have a great week, great day, great year. Thank you very much. Goodbye.